speaking, we can consider that agents is some intelligent beings that continuously perceive, decide, and act automatically. So nowadays, like many AI models, especially in the NLP community, so it's dominated by large language models. So with the advancement in the LM domain, so we can incorporate like different modules such as memory, planning, tools, actions, and so on. So all these modules forms peripheral facilities to enhance an LM brain into a comprehensive agent system. So in this case, with the help of LMs, we have a transition from rule-based domain-specific agents into like an agent which has natural language fluency, broad reasoning, and dynamic adaptability. So our motivation here is that we want to know where are we in AI research today. And so we already have powerful language models, right? We have very impressive reasoning planning capabilities, and we still have limitations in AI safety, the controllability, reliability, and trustworthiness of AI models. So what can be improved? We want to like formally present a unified framework for intelligent agents and emphasize the modularity design, the safety issue, the lifelong learning capability, and also more human style such as emotional grounding, potentials, and so on. They want to like compare human beings and machine beings and to see what is the gap and what we can do. So there's one, like the Richard Feynman said that, okay, whatever I cannot create, I cannot understand. I think for the research of AI, maybe we should say that whatever I cannot understand, I should be very careful to create. So we want to draw insights from human brain functions and social behavior and identify the gaps by comparing human cognition and AI agents. So to develop human-centered, socially beneficial AI and foster human-AI collaboration, transparency, and trustworthiness. So here, we're not saying that we should try to like copy every capability human beings have. Instead, we just want to have a peer comparison and to see what can learn from each other. So this is a table which just show a very limited aspects comparison between human beings and AI beings, right? So from the hardware level, like one is based on biological neurons, and one is more based on GPUs, energy intensive. And for consciousness, like human beings is genuine subjective experience. And for LM agents, until now, I think it's safe to say that maybe it's not conscious. And for learning style, so human is quite strong in lifelong learning, continual adaptive learning. And for LM agents, we need to be careful, and we need to do many things to make it have some kind of continuous learning ability. And for creativity, human beings are emotional, experiential, subconscious driven. And for agents, it's more statistical and data-driven recommendations. So this is not the full story, of course, but we can see there are many differences between biological brain and LM agents. And if we like try to like plot different capabilities of a biological brain and consider, okay, what is the research level and now? So maybe we can say, let's define like grossly L1 is what we consider is well developed, and L2 is, I think it's still well developed, but still we have some space to improve. And L3 is kind of rarely explored. So although the boundary is not so clear, but we can see that like the perception to different raw signals, especially language understanding, and I think also visual perception, those kind of capabilities has been well developed, although we can still further improve them, right? And for many key capabilities like reasoning, planning, memories, and so on, there are also a lot of research to improve them. And actually, we're still not very clear about how they are developed in the brain, although we have many research advances in cognitive and neuroscience. And there are also some topics which is rarely explored or under-researched, like the self-awareness, emotional processing, empathy, cognitive flexibility, and so on. So I think it's beneficial to like put as much important characteristics here and try to have an overview about it. although this is also not the full story, but it's kind of an overview. So in the research of AI agents, we still lack a unified framework. So current AI agents, they have their own different architecture design from different researchers groups. And it lacks seamless integration of perception, memory, reasoning, and action. And human brains integrated, that modular approach serves as an inspiration. So in our recent work, we first defined like general framework, try to unify different AI agent research. So these are some, I think these notations are quite common, so we can skip. We can check this figure. So if you check this figure, I think at the first glance, it's actually quite similar to what you can see in a traditional reinforcement learning agents. But we give it a more detailed intrinsic structure. So you have a environmental space S, and with state transition function T. And for this environment, it can be very complex. So for human beings, the whole world is our environment, right? And we have different sensors, so which can perceive different types of information, and which gives you observation. And based on this observation, the core is the cognition module or the cognition function ability. So we actually further decompose cognition into the learning and reasoning. Well, learning is about, okay, you have different types of the mental state. So here we define 5 different types, but for different research works, maybe they cover a part of them, or maybe they even have more richer designs. So, but here we highlight some key parts, like the memory, the word modeling, and the goal-driven, the reward, and emotional factors, and so on. So based on the observation, these mental states will be updated, and based on the mental state, the brain will reason about what potential actions to take. And these actions can have direct impact to the external world, or it's more about the mental state to guiding the following actions. And for the whole world, we can consider it combines the environment and intelligent beings, including human beings and intelligent machines, and organized by different social systems. Yeah.
I have a question about the last slide.
Yeah.
What is the difference between goal and reward?
Goal is like, you can consider goal is a motivation for you to achieve some goals in the long term. So it's your objective, and the reward is highly dependent on your goal. So if your action helps you to get more close to your goal, you have a high reward.
So typically when I see this slide, the underlying assumption is that the reward comes from the environment, but you've not put that there. Is there a reason why you've put reward seemingly inside the agent?
Yeah, we consider that all the information from the environment is perceived by the sensor. So the observation actually represents the information from the environment.
Okay, thanks.
Okay, so if no more questions, I will continue. So formally speaking, you have the environment state S, and you have the perception function P. So based on your current environment state as of T and your last mental state, well, this mental state encapsulates all the different sub-mental states we have just shown in the figure. Then you get the current observation OT, where OT represents whatever you can perceive from the external environment. And for cognition, so we further decompose it into 2 steps. One is learning. So learning is about some long-term change you have, derived from the observation. So based on your previous mental state MT-1 and the last action and the current observation, you learn from your new observation and your experience to update your mental state. So this, we define it as learning. And for reasoning, it's about based on your internal mental state, M of T, you reason about what action to do. And note that this action encapsulates different types. So it can be some explicit action applied to the external environment, which will have impact to the S of T. It can also be just some mental actions. Well, for example, you want to do some further planning and reasoning and so on. And for action, you need to transform your action source into a really executable action. So we represent it as A-T. So, and it is determined by an execution function E. And finally, the environmental state will be transit by a transition function. So we further define what we call the foundation agent. So we're actually here, we want to emphasize the ability of act as a foundational build block to construct more intelligent products. So a foundation agent is an autonomous, adaptive intelligent system designed to actively perceive diverse signals from the environment, continuously learn from experience to refine and update structured internal states, and reason about powerful, purposeful actions, both external and internal actions, to automatically navigate towards complex long-term objectives. So here we highlight 3 important characteristics. So it should be sustained autonomy, it should be able to perform adaptive learning, and purposeful reasoning. So compared to more traditional agent design you can find from a textbook, so here we actually emphasized more about the different abilities in different parts, and also we give it a richer internal mental state structure and clearly define the learning and reasoning process. So more specifically, we consider that a foundation agent can be able to perform multimodal perception, can have cognitive adaptation ability, and goal-directed reasoning, purposeful action, and multi-agent collaborations. Because you cannot expect one single agent to manage very complex tasks and very long history. Even though you can do so, it is not the most effective and efficient way to do. And we can make connections to many classical theories. For example, the classical perception, cognition, action cycle. So here we extended with explicit attention learning, different mental states. And for Minsky's society of mind, so we have modular cognitive subsystems like memories, emotion, reasoning, and so on. And if you compare to Bozaki's inside-outside perceptive perspective, so actually here they say that instead of consider your brain is kind of passively perceives the world and making decisions about actions, you should consider it as an active action machine. It's even for perception, it's a specific type of actions. So here we have the internal mental states actively shape the perception. And for PMDP, here we define more well-grained, fine-grained internal mental states. And Bayesian active inference, we minimize prediction error by updated world models. So next, let's discuss different parts like the learning, reasoning, memory, and world module. So as we discussed in the previous agent loop, we defined learning as based on the previous mental state, the previous action we made, and the current observation, we update the internal mental state MT. So biologically, human leverage specialized neural circuits for different types of learning, includes supervised, unsupervised reinforcement learning, so with different brain structures. So it's operating across multiple time scales with inherent mechanism for attention, memory consolidation, and emotional regulations. And from the AI perspective, the large-scale model and agents can learn from massive data sets, adapt via fine-tuning or reinforced and context-based adaptation, during inference. Let's check the life cycle of an LM. We have the pre-training, right? We have the post-training and surfing and utilization. In each stage, we have different sub-procedures. For the pre-training, we need to pre-process the data, ensure the data quality, and split it into train test. And we have the corresponding infra. And for post-training, similarly, we have different data preparation, bias mitigation, safety issue, continuous adaptation. And for surfing, it's more about the efficiency. And for utilization, you have different ways to interact, better utilize AI models. So actually, in this quite typical like pipeline, how to train, pre-train, and post-train a model. Like you have the pre-training for LM, and you have the instruction tuning or supervised fine-tuning, and you also have the reinforcement learning, where you train a reward model and further align the model with human values with reinforcement learning. So if you consider like unsupervised or self-supervised learning, it learns from large-scale unlabeled data, which is very good. And you can pre-train large language models based on it. It's scalable, builds general representations, but it also lacks direct task-specific feedback. That's why we also need some fine-tuning or post-training to further improve it on some specific downstream tasks. For supervised learning, it is good for downstream tasks. So it's clear, reliable learning signals, but it's also data hungry and limited adaptability, because we may have some catastrophic forgetting issue. We may need more data than we expected. And for reinforcement learning, so it's important for not only the value alignment, but also for reasoning. I think recently there are a lot of work which is trying to improve the inference reasoning based on reinforcement learning. But it's also like the concept is about the sample efficiency, and it depends heavily on the reward design. So if you don't have an appropriate reward design, like a classical joke is that if you ask AI to like how to predict the environment, maybe the most effective way it found is that just to remove every human being, right? Because this is like you also design the goal, but the reward is not well designed.
Sorry, can I ask another question? I'm a bit confused. So here you have LLM, and then you train it sequentially with 3 different ways. Like first supervised learning, then RLHF, then
reinforcement. So here is the pre-training, right? You have from the large scale data, you pre-train to get your raw language model, and then you can, let's say, perform instruction tuning to improve its performance on the downstream tasks. And you also train a reward model. So for example, this is the preference data collected from human beings or from AI labelers. Then based on it, you can use reinforcement learning from human feedback or from AI feedback. So those are quite typical ways to collecting preference data either by human labelers or AI labelers. Then based on this reinforcement learning signal, you are further align the model with human beings' value. So this is a very classical pipeline, although nowadays many models have more complex and more systematic design in the training process. But here we presented both supervised learning, self-supervised learning, and reinforcement learning.
I also have one question. Under pros, when you say encourages exploration, are you referring to reinforcement learning in general or to RLHF?
We're actually talking about reinforcement learning in general.
Okay.
Yeah, for example, if you think about reasoning, right? When you want to like solve a more complex task, it's not only about exploiting your prior experience, because maybe in your prior experience, you haven't ever met such a complex or new task. In this case, you need to explore more to find more effective solutions to new tasks.
Okay, because RLHF itself like doesn't encourage that much exploration, right? Or like the
it depends on the design of different algorithms.
Okay.
Oh, they're good. No, okay. I think you can go ahead.
Okay, so I will continue. And in context learning, so or more generally speaking, like prompt engineering, right? You can put whatever like information you want in the prompt. So it's a way to adapt at inference time by providing examples or instructions in the prompt. And you can do a lot of different prompt engineering techniques, such as like in-context learning, chain-of-thought reasoning, and many others. So there's no retraining needed. You just input the information you want in the prompt. It's flexible and quite quick to iterate. But because it's highly sensitive to prompt phrasing, like so I think there's a research paper which shows that even you just change the style of some comments and so on, it will have significant impact on the final performance of many tasks. And another popular way is what we call the PERFT, right? parameter efficient fine-tuning. So these are some quite classical way to do perf. So either you have some replay based, you have some replay buffer, and you have regularization based. You regularize over some the models. For example, you can use the LoRa and so on. And here is architecture based. So you have a smaller trainable architecture, and you froze the major part so that you don't need to retrain the whole parameters. And distillation based. From the large model, you distill a student smaller model. So those are different ways you can learn in a more efficient manner. So this is a direct improvement in task performance, but also there's high computational cost and there's risk of overfitting. And for agents, like the agent learning includes like the context level adaptation. So you're updating the agent's mental state without modifying ways. For example, like in the memory, you can augment the memory by different like prior experience, by prior skills, or RAG. It's like you retrieve the external context information based on your current input, and also in context learning. So it's fast, it's flexible, but there's also issues like the ephemeral knowledge, the limited long-term stability. So here we show that you can retrieve the different data and knowledge. You can also record different external programs like APIs, functions, softwares, or even like other neural network models as your tools, and also physical tools if you are doing some embodied learning tasks. For interactive or tool use learning, like you learn by interact. So here, like it's very helpful for real-world tasks. You can receive real-world feedback, and you can have dynamic skill acquisition, but you need to integrating external feedback, and this is actually challenging. So if we compare AI learning with human learning, so the challenge of AI learning is that the data efficiency, we need enormous data sets for generalization ability. The transferring skills is not always easy, and stability. So the long-term consistency is hard to maintain. So actually, even now, when you interact with ChatGPT or the sort of models, when your like context becomes longer and longer, it can still lost some information and get detoured to your original goal. And for reward design, so specifying the nuanced goal is also complex. And for human learning, like our human beings, we can learn from few examples. We integrate cognitive, emotional, and social cues, and also we're naturally adaptive and robust. So there are many future directions we can explore. So for example, how to unify different learning pipelines, like integrate supervised reinforcement learning and unsupervised signals, and memory-driven adaptation. So how to emulate human memory consolidation for stability, and interactive learning to enhance the agent tool and real-world interactions, and ethical data-efficient methods like minimize data use while ensuring fairness. So this is not a full list, of course. We have provided more detailed discussion in our survey paper. The next is reasoning, the second important pillar in the cognitive module. So reasoning is about making decisions about what is the next action of T based on the mental state M of T. So as we know, we call it system 1 and system 2 in human brains. Like the system 1 is more quick, intuitive, and system 2 is more well-deliberated, like conscious step-by-step reasoning. So similarly, from the AI perspective, we also consider different aspects like the depth of reasoning and the breadth, so to conduct parallel reasoning. For depth-oriented reasoning, the most classical technique is the chain of thought, right? We solve tasks step by step, and it's still very popular nowadays. So it provides interpretable step-by-step process, but it can also be slow and prone to error propagation, because like whenever you made a mistake in some intermediate steps, it will have impact to all the following steps. Right? And later, researchers proposed many more like variants, like many structured reasoning paradigm. So not only emphasize the depth, but also the breadth. So we want to explore multiple reasoning paths in parallel. So techniques like the tree of thought, graph of thought, forest of thoughts, and so on. So they're trying to utilize different reasoning data structure to manage the complexity, the breadth and depth of the reasoning paths, so that you can, instead of find a suboptimal solution or wrong solution, we want to increase the probability that we can achieve a better solution path. But it's also computationally intensive and requires pruning. Otherwise, there's a so huge reasoning space. So you need to find an efficient path. There are also domain-specific reasoning workflows. So for example, MetaGPT is an agent for software engineering, so programming. So it designs specialized reasoning pipeline for particular domains. So for example, they design specific roles like the product manager, architect, project manager, and so on. So those roles, they collaborate together, just like how a real software company collaborates. So it's highly optimized and task-specific, but it's also less generalizable and has higher engineering effort. And there are many more LLM agent reasoning approaches, like model-based reasoning. So usually, you can consider reasoning is a searching problem. You are searching in the reasoning space. So you have different operators. So for example, if you are trying to solve a data science or machine learning task, you need to choose different data preprocessing operators, the model choice, the parameter design, the evaluation methods, and so on. So at each stage, you have different choices, right? So in this case, actually, you're searching in a large space. And this is just for data science or machine learning. If you consider more general task setting, there are many complexities there. And test time scaling methods like tree of thought, self-consistency, and planning with tools and memories. So it's integration with external retrieval and simulators. So if we compare how AI reasons nowadays and how human beings reason, so AI reason, there are many challenges. The limited transparency, so it's difficult to explain and trace complex reasoning paths clearly. And there's fragile generalization, is sensitive to subtle context shift, lacks robustness across diverse situations, and resource-intensive planning. So computational demands scale sharply with task complexity and depth. So take a real use case as an example. Nowadays, many AI agents, when they want to showcase, okay, my agent is powerful, a typical example is they ask the agent to book the flights, right? Maybe, but do you consider it's reliable to let an AI agent to book your flights for now? Maybe whenever a tiny mistake is made, it will cause much more trouble than the benefits you will get, right? So the reliability is very important, especially when it involves complex interaction with different environments, with different tools, and so on. So that's the challenge here. And if you consider the strength of human reasoning, so it's intuitive flexibility, so it can rapidly integrate intuition and analytical thinking, so contextual richness, so that seamlessly incorporates emotional, social, and situational awareness. And it's also efficient multi-skill thinking, which means you can plan about a very broad and long-range things. You can also make more deliberated inference about details.
I'm curious because so far, you mostly show the challenges in AI and then the strengths of human reasoning or human cognition. If you also consider in the paper the weaknesses of human reasoning, humans are also often shown to take shortcuts or heuristics when reasoning.
Yes.
In Kahneman's paper and book, they often show this.
Yeah, we're not saying human beings is perfect, of course. The main purpose of our survey is what we can learn from human beings. So we emphasize more about the strengths of human reasoning, human brain, and we emphasize more about the existing challenges and drawbacks in the AI aspect. So, and as we mentioned that, it's not. What we're trying to emphasize is not we should learn from human beings for every aspect. It's not, and also it's not a good thing to do so, right? There's many considerations, but it is necessary to at least we need to highlight the difference and gap we have until now, and then make careful decisions about, okay, what we need to do in the next. And of course, like for example, in learning, right, we mentioned the strengths of human beings, but also like we cannot read so large amount of data just like LLM pre-training, right? This is a very obvious like drawback of human learning. Yeah, but here we are more emphasized on what is the good part of human brains, and maybe it can be helpful for the next generation AI. So the insight here is we want to closing the gap between AI's computational strengths and human intuitive driven flexibility is key to next generation reasoning systems. Yeah.
So just a comment about what they're saying. Like you say, sorry, a comment about what you guys asked, like contextual richness seamlessly incorporates emotional, social, situal awareness. What comes to mind is like impatient drivers, right?
Impatient drivers.
Yeah, like humans can be very impatient when they're driving, right?
Yeah.
And that can cause to danger on the road.
Yes.
I think like a AI can naturally be much more patient, like you said.
Yeah.
Doesn't care when it, necessarily when it gets to work or something.
Yeah.
So yeah, I was noticing that too. It seems to like focus on kind of, I think it's true, humans can do stuff like that, but doesn't mean they always do, right?
Yes.
It doesn't mean like they do it every time seamlessly. So anyway, that was just a comment.
Are you still sharing the screen because people online cannot see your slides?
Oh, okay.
Yeah, can you just share again? I think something.
Okay. Yeah, that's a good point. So when we emphasize some unique characteristics of human brains, so it can be beneficial in many cases, but it also maybe not appropriate in some specific contexts, right? So for example, even for intuitive flexibility, like maybe instead relying on intuitive reasoning, we want more like strict with guaranteed reasonings, right? So, but I think here the main purpose we want is to show the gap and to see what is missing and what can be helpful. So there are also many interesting directions we may explore, like the dynamic hybrid reasoning, which combines different types of reasoning paradigms, and hierarchical modular architecture, which integrates both general reasoning and specialized domain modules, and context-aware social cognition, which can be helpful in especially like, let's say, emotional support use cases, and efficient scalable planning and real-time adaptive reasoning. Because like when it's for an online applications, you cannot have a long like latency. And memory module. So if you check this diagram, it basically summarizes human memory hierarchy in a high-level manner. So it includes long-term and short-term memory and sensory memories. And for long-term memory, you can further decompose it into more fine-grained types. So it is a multi-type system, and it further subdivides into explicit, declarative, and implicit, which is non-declarative memories. And human memory exhibits rich diversity and adaptivity. And in terms of memory, we want to discuss two parts. The first is the representation of different types of memories. And the second is the life cycle of the whole memory system. Includes acquisition, which is like how you obtain memory information from the raw observation. Encoding is transited into more structured representation. And derivation is distill more useful, high-value information and forget the useless ones. And retrieval is when you actually need it, you need to like effectively find the relevant piece of information. And further utilization is how you incorporate this memory piece to generate better response or in many other applications. So for the representation of sensory memory, so basically sensory memory is the initial encoding and transient retention of sensory inputs. So there are many techniques like the attention-based filtering or multimodal encoding. So basically here we're emphasizing on first, which part of the information is important to the agent. So you need to have an attention mechanism, and you need to have a broader ability to incorporate information from different modalities, not only text, but also image, video, audio, and so on, depending on the use case. And short-term memory is temporary storage for immediate task-relevant data. So techniques like context management, working memories, and so on. So check this figure for an example. So here, the agent asks, how was your day today? And the human user says that, fine, my boyfriend James baked me a birthday cake. And then here is there's a system alert. Okay, this is something valuable. You should maybe store it in your memory system, right? You have a memory alert. Then you can add information like birthday is February 7th and boyfriend's name is James. Then let's say you have another conversation. So did you do anything else to celebrate your birthday? And the human user said, yeah, we went to Six Flags. Okay, Six Flags is some interesting named entity. Let's try to retrieve the relevant information from the memory. And maybe you find some information like James and I actually first met at Six Flags. And based on it, you generate your response. Did you go with James? It's so cute how both met there. So in this case, like with those memories, you can make your chat more vivid and engaging. And for long-term memory, we emphasize more about the long-term value. So it's about durable information storage, enabling knowledge generalization. So techniques include like semantic and episodic memory integration and procedural memory storage. So here we show an example of the memory bank. So here they have the past conversation, and based on the past conversations, they have the event summary, and also gradually complete the user profile. And then all these are stored. They will update the memory into the long-term memory system. And they also implemented the forgetting curve to forget outdated information. And based on this, you can retrieve the long-term memory. You can know better about the users and support your different applications. And here we mentioned the AAG, the 32 is one work in our team, which is about analogy-based retrieval, so which is modeling the procedural information or procedural memory and retrieve it with analogical thinking. So we talked about the representation of memories. Now we talk about the life cycle. So from the acquisition, so acquisition is about capturing the raw environmental inputs with a preliminary filtering process to prevent cognitive overload. So here the challenge is that you have a vast volume and complexity of data. And in this data, you can have redundancy, you can have irrelevant or unimportant inputs. So there's need for rapid, loosely filtering to highlight the potential relevance. So in this case, you need to compress the information, you need to filter out the noise, and you can utilize experience consolidation to better incorporate them. And we also mentioned the multimodality to incorporate diverse information. And encoding is more about transforming the raw observations into more well-structured representation. So for example, you have knowledge graph, you have vector database, and so on. So the challenge is you have high dimensionality and noise in your raw inputs, and integrating information across multiple modality is also important. So key techniques include, but not limited to, selective attention, which is about paying attention to the valuable part, contrastive learning, which is about aligning the different modalities to have a more well-aligned representation, and multimodal fusion to better incorporate different types of data. And derivation is not only remember what you observed from the environment, but also uncover the hidden part to reveal the implicit information contained in these observations. So challenges include the dynamic evaluation of important information value, maintaining efficiency while preventing overload. So the techniques like reflection, summarization, distillation, selective forgetting, and so on, all of this is about drive new information from existing ones and remove low value information. And retrieval, if you don't interact with your memory, then it's useless, right? You need to retrieve the relevant information and incorporate it into your application context. So retrieval is about efficiently locating and matching relevant memory fragments. So we need to deal with different types of memories. The context alignment, we need to have deeper semantic match beyond simple keywords. So you cannot just retrieve memory by just keyword overlapping or string similarities. And even for vector database, it's still not enough in many cases. So you need to uncover more analogical or more high-level relations between different information. And there are also real-time constraints. If you're in a conversation, you cannot spend, let's say, more than 10 or 15 seconds to retrieve the memory and let users wait. Right? And also dynamic updates. You need to ensure timely and accurate memories as new data arrives. So many techniques. So I want to name them. I don't name them one by one, but this is a very important research field about information retrieval. A utilization is applying stored memories effectively to enhance your downstream tasks. So the challenge is about balancing the large memory stores and effective use, and the abstraction and generalization of specific memory segments, and also avoiding hallucination and incorporate incorrect content in the outputs. So here, one interesting example I want to say is about, so for example, if you think about, let's say, chemical reactions, maybe you want to retrieve some information from chemistry or from material science, but in a more high-level manner, maybe you can make connections between how you cook a dish, right? So they all involves different steps, and to make a chemical reaction happens, you also need to take care of the portions of different materials and so on. So in this case, you're actually making connections between them in a more high-level abstraction. So if we compare human memory and AI agents, so human memory has rich associative recalls, the flexible abstraction, intuitive generalization, and adaptive forgetting. And for AI agent memories, right now it's explicit and structured, and there's limited associative recall, and it's data-dependent generalization, which requires extensive training data to struggle outside trained scenario, and rigid or narrow forgetting. So typically, the current AI agents lack dynamic mechanisms to prune outdated or irrelevant information. So the most simple way people doing that maybe just follow a fixed forgetting curve and so on. Yeah.
This on? Okay. Maybe this is more of a comment. I'm going to take issue with especially the second bullet point under AI agent. I challenge you against ChatGPT and your associative recall and say any fact at all on Wikipedia. I mean, it seems to get associative recall. You know, you reference anything and it's going to give you a reasonable completion. Why do you say that it struggles to get this in this context when at least relative to human memory? I think we struggle with associative recall much more than they do.
Yeah, I think maybe this is arguable in this part. I agree. So I think here we are more emphasizing on the retrieval part. So if you design retrieval algorithm, so right now the mainstream is you have a vector database and you calculate the similarity by the embeddings. So if your embedding is not good enough, it's hard to retrieve a more semantically relevant but textually it's not so similar piece of information, right? So in this case, it's not directly, if you consider the associative capability of AI agents, it's the agent itself, it's the internal model memory. It's not making association between the query and the external memory module. So I think this part may be confusing.
Okay.
Yeah.
Thanks.
Maybe I need to reshare it. Yeah, I think whenever this.
Share the slide.
Okay, this is.
Okay, can you share?
Yeah, I can share.
Can you share the?
Yeah.
Okay, hold on.
Yeah, so I would say AI agent or LM model itself is quite strong in the second part. Yeah, but for the retrieval module we have until now, I think it can still be improved a lot. So we can further develop or improve the neural-inspired recall and also the metacognitive curation, for example, employee reflection to detect inconsistencies and refine knowledge, using abstraction and synthesis to distill key insights from experience, and also improve the adaptive memory management, like practice selective context-aware forgetting to prevent overload and reduce noise, and maintain frequent updates for relevance, leveraging robust data-driven feedback loops. So I think this part is more a combination of both research and engineering effort to design a very effective and helpful memory module. So different research directions include like the neural memory network, metacognition, episodic memory enhancement, and cross-model context-aware systems. So I'm not going to discuss each bullet in detail due to the time constraint, but I want to show one recent work from our research team, which we call the R3MEM, the reversible context compression memories. So here the idea is that we want to, instead of build an explicit memory module, like you are trying to store the memory in string or vector database format, we want to learn a memory network. And how we do it is combining two ideas. One is combine both short to long and long to short pre-training. By short to long, we mean like from, let's say, word level, phrase level, to sentence, paragraph, and document level. And long to short is the reverse direction. So the idea is that, let's say, when you do the pre-training, you can predict the subpart from the more broad context, right? If you do the retrieval, you're actually trying to retrieve the broader context from the limited hint to query part. So that's why we have the short to long and long to short bidirectional pre-training, and which requires us to use a reversible model. We actually utilize a reversible transformer model to do this. And we incorporate virtual memory tokens at different levels to incorporate such memory information. And by combining these two ideas, we found that such a memory model actually outperformed many existing memory models, which is also, this paper is also public on arXiv. And the last module we want to briefly discuss is what model. Yeah.
Sorry, can I ask a question about the other? So,
yeah.
What are other like models that are used for memory, like except this one? What is like the second state-of-the-art one, for example? Like, can you say a bit more about other models that are used for memory, like to compare the how they are trained?
Other models?
Yeah.
I think the most classical work is Turing machine style models. You have a memory network, you have different memory slots, and you retrieve like store the memory as vectors in the memory slot, and you retrieve by read and write, right? So this is, I think, is similar to the concept of memory in a computer, and it also have relevance to the vector database. But here, like we are more emphasizing on how to train. Like you can consider it's a llama model, but we changed it to a reversible transformer architecture, and we make it specially served as a memory module. So the main functionality of this revised llama module is to serve as a memory network. So that is the difference. I think for existing many research, either you have a memory database structure, or you also have some memory layers in your network, but the design between our work and the architecture is different. Yeah, you can check the paper to have more detailed information. Yeah. And what models? So basically, what model is a high-level abstraction and simulation of the external complex real world in your mental state, right? So it's a mechanism to predict and simulate future states without direct trial and error. And it approximates environment dynamics through learned or given functions, serve as the basis for planning and adaptive behavior in AI agents. So this figure is drawn by both ChatGPT and myself. It's a collaborative work. So with what model, you can plan ahead by simulating potential trajectories. You can reduce the reliance on costly trial and error and unify insights from cognitive studies with AI implementation. And we want to enable agents to handle dynamic and uncertain environments. So it's like basically before you actually do some actions, you can like mimic what will happen in the future in your brain, right? For example, when you are doing sports, like you choose your pose, you choose your speed and actions and so on, because you predict, okay, by running to this place and with this direction, I can hit the ball and it will go somewhere else. Right? So this is based on your prediction about the future. And when you plan for a more complex task, you're like mimicking the potential results in a more long-term future. So we can define it as there's a two-step. So based on the state and action, there's a state transition. Based on the transitive state, you turn it into an observation. So the first is the transition function, which is the state evolution under actions. And the second is observation, where you can observe the observable signal based on the latent state representation. So what model learn or use approximations of this transition and observation function to predict future states or observations? And based on this framework or this formalization, you can classify the research about what model in about these different categories. Like the implicit one, you have a single latent model encapsulates the transition of observation. And it's often trained end-to-end with minimal factorization. For explicit, you have factorized the transition and observation module. So there's a clear separation of concerns and make it more interpretable. And simulator-based, you have external simulator to simulate like the real-world interaction. And the agent learn by running trials in a controlled or real environment. And there are also many other hybrid or instruction-driven methods. So this is one classical work about what model with the implicit paradigm. So here you have the visual encoder, the V, and you have the memory RN to update the visual encoder's inner representation. And you also have a controller based on the state you control, what is the action to take. Right? Okay, we just have 5 pages. Yeah. So the pro is simplicity and compact repetition, and the con is you have less interpretability and difficult to enforce domain-specific constraints. And explicit paradigm. A question? Yeah.
I was wondering, like, if we can use LLM as learning this mapping of like VLM type, like, but not like translate to the text, just like learning the dynamic through like LLM. Is it possible, like VLM or something like that? You know, the whatever abstract representation that they learn through language, they can like generalize to predict the state predictions in the environment.
Yeah, you mean you're asking whether we can use an LLM to predict the transition of the state, right?
Yeah, not necessarily like translate it to language, but using those abstract representation.
Yeah, I think actually this is plausible, and it's also an idea in the reasoning domain. So instead of trying to decode every output token, we perform what we call the implicit reasoning, right? Actually, this is reasoning in the latent space. And similarly, like reasoning is predicting the tokens in the latent or the text space. Similarly, for the state, you can also predict in the latent space, or you want to predict explicitly the next frame is also like there are different choices. But as you said, yeah, it is possible to do that. Yeah, not decoding the obvious output, but also just use the hidden representation. I think definitely there are many such works. I think you can check the citations in your long-survey paper. Yeah, I only provided some citations in those slides, but this is definitely not the whole story. Okay, I only have a few minutes. And this is about explicit paradigm, which separates these two parts, observation and the encoding. So the point you require more data and careful tuning and vulnerable to errors if the approximated function derived from reality. And simulator-based. So that is simple. You have a simulator which can actually let you do the actions and simulate the future. But of course, it will be limited to the fidelity of the simulators, right? And it's also computational cost. And also hybrid and instruction-driven paradigms. So what model also has close correlations with other parts like memory, action, and perception because it provides information about the future and supports the cognitive functionalities. Right? So compared to the brain, human cognition exhibits multi-scale adaptive prediction and integrated perception, memory, and action-inspired AI designs. The core challenges here includes like balancing the model complexity with predictive accuracy, achieving long-term stability in dynamics, real-world setting, and overcome the simulation to reality gap. So this is the takeaway for today's whole talk. So we introduced a general formulation of AI agent loop. We conducted a parallel comparison between human brain and AI agents. And by examining the current status of agents research and drawing inspiration from human brain, we want to gain insights for the future research. And this is the title and the link to the archive paper we released yesterday. Thank you, everyone.
Thank you. Thank you, Bang. So are there any questions for Bang? Either in person or online? Okay, we don't have any questions. Oh, maybe we have one. Can you speak up, Yuchen? Okay, we cannot hear you. Can you type your question on the chat? I think it's gonna be better.
I think I just raised my hand by arrow.
Oh, okay, no worries.
Okay, do we have more questions?
Yeah, just kind of going along with some comments were made. I like your presentation.
Thank you.
But like, is there any do you do any thoughts about how maybe humans are I guess in more than the obvious sense, like how we're not as good as computers, say, or like AI agents, but there's some ways I think that maybe AI agents could be more consistent or right than humans. Like we have to sleep every day, right?
Yes.
That's an obvious thing, but I think anyway, I think a lot of us are a little bit amazed with LLMs still, and kind of like I think there's also subtle ways where they can outperform humans or be better than humans. I don't know if your group explores any of that.
Okay, so you mean like in which part?
I say something more human, like say patience, for example.
Patience.
It's something I've noticed, like in a car. If you've been in a self-driving car, this self-driving car can wait maybe for multiple red lights if there's no safe path. And that's fine. And that's what we should do too. But I think people would be more apt to try to find a shortcut around it because they're impatient. Right?
I think that is the cause of human emotion, right? We don't have so long patience as machines because we're impacted by human emotion. But in the meantime, the emotion also drives our goal, drives our learning, and motivates us to do many things. So this is a two-sided blade. It helps us. It also brought us many like bad effects as well. Yeah. So that's why.
Yes, that's a good point, because we're impatient because we're trying to do something, right?
Yeah.
Right.
And also, this is very, I would say, until now at least, it's a uniqueness of human beings, right? We have feelings, we have the emotions, and that makes the humanity.
Yeah, you said that like people, the AI agents aren't like driven to, like they don't have
Yeah.
I don't know how you said that, but they're not like driven to do something, right? They're not motivated themselves.
Yes.
Right.
Yeah. And also I think maybe we need to be careful to which extent we should let them motivated by themselves, right? Maybe they cracked the goal and something uncontrollable happened. So that's why we're emphasizing that we're not trying to encourage, okay, let's replicate every characteristic of human beings and let the machine have it. We just want to make a parallel comparison to have a critical thinking about, okay, what's going on? What's missing? What is their better? What's our strengths? And what's our mutual weakness and so on.
Okay, thank you.
Yeah.
I really enjoyed your presentation. Thank you. There was one point about multi-agent collaboration.
Yeah.
And then you also made a comment about how, for example, booking flights, a very small mistake could cost you a lot. And so I wonder, in the context of sort of like multi-agent collaboration, a small mistake, does that sort of trickle down to all the other agents? And how do you sort of manage one agent versus a group?
Yeah, that's a good point. So actually in this part, today's talk, we didn't cover the multi-agent part. This is the part 3 of our long survey. So we only covered a small portion of part 1. Yeah, but for multi-agent, as we said, like even you have a superpower agent, maybe you don't want such an agent, single agent, to do every task for you. First, it's not the most effective, and it's also not the most reliable way. For multi-agent, the thing is like you need to have a good way to decompose the role, decompose the complexity in different situations, and this should be automatically happening instead of relying on many human design templates and so on. Right? So, for example, we saw the software engineering agent like the MetaGPT and many others. So they have well-designed workflow for this application scenario. But if you ask it to do like flight booking, is another workflow and so on. So that's why there are many research about how to automate this workflow in different tasks. And aside from this complexity decomposition, similarly, you need to manage the errors, the different things happening during this process. You cannot trust, okay, every step you will do it correctly. Of course, the errors will happen and reflections is needed. So you need to have some variable mechanism to check, okay, this subtask, this step, it is finished. We should trust it. And then we should have an overall state management to gradually track the state.
Thank you for your great talk. And I have another question. As far as I know, there are 2 points of views on how can we develop AI system, AI agents so that they can think. The one point of view says that we hope that our design agents can think like human. And another point of view says that we hope that the agents can think rationally. They make less mistakes than human.
Yeah.
And what is your point of view?
I think this is task dependent. So let's say if you're asking an agent as an assistant to solve real-world tasks, you hope that it is quite objective. It's not impacted by subjective emotion and so on. It should be accurate, efficient. But if you are doing something more like involves more empathy, more emotional support, you hope that it can understand the human's feeling, right? It can understand the social context and give you emotional support. So that's like, you can consider, okay, shall I like act like human beings with emotional feeling? It's also a decision to make for by the agents, right? Because it's like in different contexts, you're switching between different modes. Yeah. So that's why I think we cannot say whether you should choose A or B. it's like it can switch between different modes.
Yeah. So, so the question is, how can we find the mode that we need to switch to? Is that should it be a part of human labor?
I think it should be. It's also a decision to make. So it's a decision-making process. So the agent should be able to recognize the context and to decide to how much extent I should be rational or to how much extent I should be more empathic, emotional, and so on. So also another way is like maybe you have more specialized design instead of trying to have a unique agent which can provide help in all the use cases. Maybe you have more specialized different agent types.
Okay, thank you so much for your answer.
Okay, if there are no more questions, you can thank again, Bang. Thank you for the talk.
Thank you very much.
And yeah, see you next Friday if you come for the next talk.
And thank you, every audience online. Till next time.